otherwise I'll forget. So no, the tests are not marked. They're on my radar. Yeah, I wanted to have them done, trust me. But I also did not have time to make an assignment for you guys, so you're home free for the long weekend. So works out. So today we're actually just going to touch down in chapter 2 for polynomials. For some reason we need to know how to sketch and move graphs of a polynomial just briefly. So we're just going to get in, get out. Tried to thin the herd as much as I could, but there's still some stuff that it's like, oh, we need to talk about this. So yeah, so just in and out of chapter 2, and then we're on to chapter 5, which is just more about functions, more like function composition, but we'll talk about that on Tuesday. Any questions before I start? No. All right. So chapter 2. Is on polynomial functions. Everyone likes a polynomial, right? Who can go wrong? We've seen polynomials, right? Ax squared plus bx plus c is a polynomial. Even a linear equation, mx plus b, is a polynomial. Right, but we're just going to build up these polynomial functions a little bit. And so section 2.1, which is the only one that we're doing, is graphs of polynomial functions. So polynomials are just the sum of monomials, which are just the single terms in there. And so what we're going to do is we're going to talk about the behavior of monomials and then build into polynomials, because they behave the same. So we begin by considering monomial functions. I feel like I'm forgetting something. Is there something I usually do in class? I feel like, yeah, I'm recording, I'm doing all, anyways. You know when you feel like you've forgotten something? That's me right now. Anyways, we'll start with the definition of a monomial function. So a monomial function is a function of the form f of x equals b, or more importantly, f of x equals a to the x to the power of n. Where a and b are real numbers as long as a is not equal to 0, right? Because then we'd have f of x is equal to 0 times x to the power of n, which is still just 0, so that's not helpful, right? And so as long as a is not 0, and n is in the set, remember the notation, in the set of natural numbers. So natural numbers, we do a capital N and then just draw a little kind of fancy line there. Okay. I'll do a separate note for the natural numbers, but for now we'll just finish this one here. So the domain of a monomial, you might have guessed already, the domain is usually just negative infinity to positive infinity, right, which it is for a monomial. So the domain of a monomial function is from negative infinity to positive infinity. Here, I'll just clarify, n is the set of natural numbers which are the set starting at 1, going up by whole numbers 1, 2, 3, 4, on and on and on, and set. So we'll only talk about powers of 1, 2, 3, 4, 5, 6, blah, 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 blah. Right. I guess this is a definition here. A polynomial, like we said, is just the sum of monomials. So a polynomial is the sum of monomials, as the name suggests. Right? Poly means many, mono means one. So if we're able to graph a monomial, right, then we have a pretty good idea of what a polynomial might look like, right? And so we'll talk more about that. But so if we are able to graph a monomial, we will have a good idea of what the graph of a polynomial will look like. The thing about polynomials is, depending on if the power is even or odd, it's going to behave differently. Okay, and so a monomial f of x is a times x to the power of n will behave differently depending on whether n is even or odd. So we'll start with if n is even, because this one we're kind of familiar with, comfortable with, right? So think about if n is even, you could have a is 1 and x is to the power of 2, right? Then we have x squared. We know what x squared looks like. And so what we get is, we get kind of, let's see if I can draw it, x squared. Something like this. But if we go to Desmos and have a look at x to the power of 4 and x to the power of 6 as well, right? Just even powers. Let's see if I can find. Oh, it's really thinking. Okay. So if I do x squared, right? You've got this, the shortcut to the squared button here. looks like what we thought it did, right? If I do another one here, x to the power of, and if you want a different power, you use the a to the b button, to the power of 4. And let's have a look at x to the power of 6. Okay. So what happens, right, and they're kind of indicated by their colors, right? So we've got x squared here, kind of just touching briefly at the origin and then taking off again, wide, right? And then as our powers increase, what's happening is that it's just getting flatter and flatter around the origin, right? So getting flatter, but also getting narrower and narrower and narrower, right? So the blue one is x to the 4, so it's still a little bit wider. X to the 6 is a little bit tighter, but also sat down kind of harder on the axis, right? And so what happens is we have the same shape regardless, but it's just going to be how narrow and how kind of flat at the bottom is it going to look. Yeah. I wonder if I can screenshot this. I don't know. And then bring it in. Anyways, I'll do a quick sketch here, but it won't be very good because well, there's no axes. And they're not really comparing to each other. See Desmos. But what happens, right? So just to describe what happens, that as n increases, x to the power of n, let's say, flattens between x equals -1 and x equals 1. And that's just how, because of how these powers behave when the x is a decimal, right? So between -1 and 1, right, you've got decimals, right? And so they behave a little bit differently. So that's why it's flattening. And then, and what should we call these? The arms? I'm sure they have a technical term, but, and the arms become narrower. Just like x squared, x to the power of 4, x to the power of 6, as long as you have an even power, right, what happens with a negative x? A negative x is just going to yield a positive value, right? So it basically just ditches the negative, right? And so for any even power, that's how it's going to behave. And so we know that any even value of n will only yield positive values of x to the power of n. And we can see that here from the graph. My really bad graphs. Wait till you see my odd power graph. So it will only yield positive values of x to the n. So the range is inclusives of 0 all the way up to positive infinity. Okay. I was going to talk about, but I think I can cut it. We're all for cutting, right? Symmetry, etc. No. I'll only ever test you on things that I have talked about, unless it's a bonus question, and it's things you know. So let's skip the symmetry and go straight to if n is odd. Like I said, if you didn't like my graphs before, you're definitely not going to like these. We're only going to look at n greater than or equal to 3, right? A power of 1 is just kind of boring, and it behaves the same, but a little bit, it looks a little bit different, right? And so let's have a look here. Let's see if I can copy Desmos instead and put them all on the same graph, use different colors. Well, we'll see here. We'll see how it goes. All right. So first, I've got x to the power of 3. Okay. Then I'm going to do x to the power of 5. Now, obviously, I'm just drawing these. There are no points or anything, so. But it also gets narrower and flatter. How am I going to show that? I really made my x to the 3 really flat already. Anyways, x to the 7 is going to get weird. How am I going to make it narrower? Anyways, I'll let Desmos do the work. Here. How about change this to x to the 3, x to the 5, x to the 7. I'm sure you guys can do a better job of drawing these, right? If I zoom in here, that's hard to draw. Okay, so I definitely shouldn't have made my first one so flat, right? My x to the 3 should have just kind of touched on here for a little bit and then left off. But the idea stays the same, right? We think we have this kind of, I want to call it an S curve, I don't know. Right, we've got this little curvature here, and then it gets flatter around the origin, and these things get narrower, right? So they tighten up as your power increases. And so that's what they look like. And I mean, any odd power, that's what you're going to look like. So was anyone able to draw that successfully? Not I. But I think I know the problem is my x to the 3 was too. I think I need to make it more like. There, I can compete with that. How about that? Okay, here we go. Narrower, but not too narrow because I need to have x to the 7 on there. And touching a little bit more. I'm doing it. I'm really doing it, guys. Oop. Oh. Notability is clever sometimes. There. Give up. Same idea. Same same description. Okay, so that's the shape for the odd power. And so as we see, a similar pattern. I don't know why I said as. I can ditch that. We, capital we, see a similar pattern as n increases, x to the power of n flattens. I'll just write over -1 to 1. And I'll call them arms. I used to have, I don't know, I'm sure it's all over the internet, but I used to have this printout in my office where it's like my favorite dance moves, like x squared, x to the 3, sine, cosine. How do you differentiate? I don't know. They look the same. But anyways, let's call them arms, because then you can think of your dance moves. And the arms become narrower. Here, as we see, the range of x to the power of n, if n is odd, the range here, well, it's just going to keep going and going and going. Oh, come on. Oh, it's on here. Falling apart. Okay. As we see, the range of x to the power of n, if n is odd, will be -infinity to infinity. Oops. So just like we did with absolute value functions, quadratic functions, we're going to learn some kind of tricks to sketching these things, or at least to moving them. Stretch or a question?
So when we said at the beginning that f of x equals b and then f of x equals a to the power of n,
yeah,
are they interchangeable or does it depend on the?
So b would be like a constant, and so a constant is considered a monomial, but we're only talking about when we have an x involved, like ax to the power of n. But in these, like here, x to the power of 3, x to the power of 5, x to the power of 7, I'm just letting a be 1, right? So, but now we'll incorporate a's and a little bit more. So, like we did with absolute value and quadratic functions, we can develop a general formula for graphing capital F of x is a times x minus h. Hey, that looks familiar, right? To the power of n plus k. We graphed a times x minus h to the power of 2 plus k, right? So we looked at the quadratic. Right? The absolute value is a little bit different, right? But we've already looked at these. There must be a reason that they don't talk about the vertex. I think because we're going to be moving this thing around, and so I don't know. But this is what always threw me off in school when I was graphing these. I hate graphing functions, by the way. I don't really see the point. But anyways, here we are. And so this is what threw me off in school, is whenever we have so x minus h, what you'll notice is that if you have x minus 3, it actually shifts it to the right 3. It kind of does the opposite thing, but then it does what you expect it to do with the plus k on the end. So if it's plus 3, you move it up 3. So it's a little bit weird. But anyways, so we'll go through kind of the steps, because what we're going to do is we're going to start with, so if you want to graph something like 3 times x minus 2 to the power of 4 plus 1, right? Then what we do is we just start with x to the power of 4, right? So we start there, x to the power of 4, we know what that looks like, and then we'll gradually build out to this, right? And so to graph f of x equals a times x minus h to the n plus k, we will start with the graph of x to the power of n and manipulate it following these steps. One, I'll do what we're going to accomplish, right? So we're going to move from y equals x to the power of n just to y equals x minus h to the power of n, and what that looks like on the graph. So to move from y equals x to the power of n to y equals x minus h to the power of n, what we do is we add h to the x coordinates of each of the points. Usually what we end up just doing is kind of picking key points, maybe 3 key points, and just looking at how those 3 points move, right? And then we can kind of connect the dots. So add h to the x coordinates of each of the points on the graph of f. On the graph of f. This results, oops. This results in a horizontal shift to the right if h is greater than 0, or left if h is less than 0. Okay. So here's where you need to kind of like disconnect, because even though you have x minus h in your formula, right, you're just going to add h. So you're going to figure out what h is and just add it to your x coordinates. And then that'll be the move that you want. Okay. So now where we're at is y equals x minus h to the n. What we're going to do next is we're going to multiply by a, right, to get a times x minus h to the n. And so to move from y equals x minus h to the n to y equals a times x minus h to the power of n, you're going to multiply the y coordinates of each of the points, right? It says each of the points, all the points, but really, again, just keeping an eye on those usually three key points can kind of tell us what our graphs look like. Multiply the y coordinates of each of the points on the graph of y equals x minus h to the power of n by a. This results in a vertical scaling But just like before, right, if a was turned negative, right, it flips our graph upside down, right? So same idea, but may also include a reflection about the x-axis if a is less than 0, right? So if a is negative. And then our third step, right, is adding that constant term. And so step 3, to move from y equals, oops, sorry, I forgot the a times x minus h to the power of n to y equals a times x minus h to the power of n plus k. We're going to add k to the y coordinates. Add k to the y coordinates of each point on the graph of y equals a times x minus h to the power of n. This results in a vertical shift up if k is greater than 0. So if k is positive, you move it up, and down if k is less than 0. Oy, it's a lot. I guess we better put a box around it. It's a big box. Let's do an example. Graph the functions. Label 3 points on each graph. State the domain. So state domain and range. Using interval notation. So the first one we're going to look at is f of x is -2 times x plus 1 to the power of 4 plus 3. And then a little bit trickier, we'll look at g of t is 2t. 2t minus 1 to the power of 3 over 5. Right. How about, I'll let my pencil charge for a little bit while you try it on your own, and then we'll go through them together. I'll only let it charge for a little bit. Just work on A for now, how about? You can go through. Oh. What? That's okay. Then you don't have to do any work on your own. Oh, is this a fancy new one? Yeah. Let's see.
She's not. She's not.
How do I link it up?
I think she connected to the side and then opened Bluetooth preferences. Oh.
I know.
Yeah, it's Bluetooth versus whatever.
Oh.
Maybe
Okay. Okay. No, just exploring under pressure. No big deal here. Bluetooth, Apple Pencil. There's a lot of KL. I actually think, because Jason was talking about his new one doesn't work with his old one. I think they've done something
special. Something happened.
Thanks, anyways. But how are we doing for my pencil here? 10%, hey, we're up. Not that bad. 10%, we can make do. All right, let's do A together, and then I'll do it a little, give it a little charge, little boost. All right, so for A, right, if we're just boiling this down, right, we're gonna start with x to the power of 4. And so x to the power of 4, that's an even power, so we know we're gonna have this kind of parabola. Right? And so we start with x to the power of 4. If we think about which points to pick, right? What if we let x be -1, 0, and 1, right? Those are easy to deal with, right? So to decide which points to keep an eye on, let's try x equals -1, 0, and 1 and see what happens. Right. So if we have y equals x to the power of 4, right, then if x is -1, then y is going to be 1. If x is 0, then y is 0. And if x is 1, y is 1. Huh? So we can draw these. We'll start at 0, 0. And then I'll have kind of a point arbitrarily here at -1, 1. And a point here at 1, 1. Those are a bit wonky, but it doesn't matter. Hey, not bad. In f of x equals -2 times x plus 1 to the power of 4 plus 3, a is -2, h is -1, right? Trying to match it to that a times x minus h to the power of n plus k, right? H would have to be -1, and k would be 3. And so the first step, right, that we have to do is, well, we had our list, right? But we're going to add h to each of the x coordinates, right? And so these are our x coordinates here, -1, 1, 0, and 1, right? And so to each of these, the y's are going to stay the same, right? We're just talking about a horizontal shift, right? And so we're going to add -1 to each of these, right? To each of these x's. And so step 1, add h equal to -1 to each of the x coordinates. Bless you. So I guess I'll just draw a new one here. I know it's not fair because I can copy and paste, but I just can't have them on the same screen, it seems. So it's going to be nice to just be able to have them. Right, so this is y equals x to the power of 4. If we're going to add -1 to each of these, right, then this coordinate becomes -2, 1. 0, 0 becomes -1, 0. And 1, 1 becomes 0, 1. So we'll draw a new graph where these are all shifted over. Just gonna bump this so it's on a line. Oh, pen. So our new origin is at negative 1, 0. We've got a point at negative 2, 1. And we've got a point at 0, 1. So this is y equals x plus 1 to the power of 4. Step 2, multiply each y coordinate by a. So again, I'm going to steal this guy because I can. Copy. And I'll have to paste them down here because there's a page break. You know what? Just move all this so it doesn't look weird later. So if we're just looking at the y coordinates, right? So now we have to multiply by, what was it, negative 2, I think, right? So each of our y coordinates, so 1, 0, and 1, have to be multiplied by negative 2. The x's stay the same, right? And so now we're going to have negative 2, and then 1 times negative 2 puts us at negative 2, so that's going to be a negative 2, negative 2. Yeah.
So you wrote h is equivalent to negative 1, but in the equation it's plus 1 is x's, plus 1 is shifting, minus 1 is shifting, right?
Yeah, and because we're comparing to the general form, which is this one here, right? A times x minus h. And so if we have x plus 1, then h must be negative. Right? And so we're always comparing to this general form, right, to find out what h, a, and k are.
So then if h is a negative in your actual formula,
Yeah.
then is it going to be same h, or sorry, a times x minus negative h?
So that would be, so if you have x minus 3 here, then h is 3.
Okay.
Right? So it just depends on, so you want to make sure that that negative from this formula, right? Yeah, essentially. Yeah. Good. Good things to keep track of. So now what we're doing is we're going to multiply each of these y's by negative 2, right? So this one flips down to negative 2, negative 2. Negative 1, 0 times negative 2 is still 0, so it's going to stay where it is. And then 0, 1 times negative 2 is negative 2, so 0, negative 2, right? So it takes into account that kind of the flip. Right? And so here, this becomes negative 2, negative 2. This stays at negative 1, 0. And this one becomes 0, negative 2. Run out of room a little bit. So if we draw this, did I do anything? No. Fresh. we've got that point at -1, 0 still. And of course, without axes, it's hard and kind of weird, but that's okay. -2, -2. Let's say it's here. And 0, -2 is here. So now we've got this going on. So now we've got y equals -2 times x plus 1 to the power of 4. Which brings us to step 3, where we're going to add k equals 3. Oh, you know what? I'll just clarify here. Multiply each y coordinate by a equals -2. There. But I think we had k is plus 3. So add k equals plus 3 to each of the y coordinates. So again, I'm going to not so beautiful graph. So we're adding k equals 3 to each of the y coordinates. And so now this guy's going up to -2. -2 plus 3 is 1. -1 and 0 plus 3 is at -1, 3. And this guy gets bumped up to 0. -2 plus 3 is 1. So finally, our graph is at, let's put it here, -1, 3, 0, 1, and -2, 1. So now we have y equals -2 x minus, or x plus, sorry, 1. I think, yeah. To the power of 4 plus 3. We did it. Yay. Fun, right? How about that other one? The other one is going to be a little bit different, right? Because it's not actually in the form that we need it to be in order to apply those steps, right? So first you need to change it a little bit to be in that form, right? And so remember, we've got g of t is 2t minus 1 to the 3 over 5. We need this in the form f of x equals a times x minus h plus k, to the power of n, in order to apply the steps. Keeping that in mind, I do want you to work on this one for just a little bit while I charge my console. But also because it's good.
Okay, so just do bracket.
Yeah.
I don't know what the here. So right now you're just trying to bring it to this or just one. Because the only way we can do this is if we have some way to do these steps. Okay.
And that's what you expect.
Yeah. And when we're doing this, we're just it's just cheap. Okay.
Yeah. And the negatives, like even though you couldn't see it before graphing, it actually changed
Yeah.
lights up.
I said that and I was like, okay, let's
Wow, you guys are graphing away, huh? Yeah, classic. Give you guys time to work on stuff. No, that's okay. I know it's supposed to be like, you have to give them time to work on things. Like they never work on stuff. Let's do it together then. So we've got g of t, 2t minus 1. Do you guys figure out how to make this look like we wanted it to? So the trick is, at least we're honest here. No. We can rewrite this as 1 over 5, right, times 2t minus 1 to the 3. There's so much air going around, I don't know. Like, it just makes so much noise. Not air, I know, right? Sorry. My stomach's, I'm hungry. Okay, so we pulled that -5 out front. That looks better, right? This looks like it could be a, and then, but then we've got this 2t in here still, right? And so we want to pull out this 2 because we can only have t minus 1 or t plus 1 or t and then something, right? And so we have to pull out this 2, which means we have to pull it out of the -1 as well, right? And so essentially what we have to do is we want to factor out a 2, a common 2. And so we've got 1 over 5, and then bracket, and then 2, I'm pulling it outside, and then another bracket, t minus 1/2, all to the power of 3. Right, what you'll see is if you multiply this back in, 2 times t, that gives us 2t, and then 2 times -1/2. 2 over 2 is 1, minus 1, right? So you just always want to make sure if you pulled something out, you want to make sure that it can go back in and it stays the same, right? Otherwise you did it wrong. So now we can say, okay, well, we can think of this as one term multiplying another term to the power of 3, right? Because we're multiplying inside here, we're allowed to bring this 3 power on top of here. If we just had these, we can't bring the 3 inside, right? Because that's different, right? But because we're multiplying 2 terms, we can bring that 3 power on top, okay? So what that looks like is we get 1 over 5 times 2 to the power of 3 times t minus 1/2. I'll just do a little 1/2 to the power of 3. Okay. It looks like what we were working towards. It looks a little nasty, right? But that's okay. Because now 1 over 5 times 2 over 3, we can just simplify as 8 over 5, right? 2 to the power of 3 is 8, and then over 5 is 8 over 5. So we get, but maybe I'll slow that down a little bit. 1 over 5 times 8 times t minus 1/2 to the power of 3. Which we can rewrite as 8 over 5 times t minus 1/2 to the power of 3. Nice. Now it's in the form that we need, right? Nothing to it, guys. But we'll get better at manipulating things like this, right? And so we see A is 8 over 5. H is 1/2, right? Because we want to have t minus h, and so h is just the 1/2, right? And n is 3 and k is 0, and that's all right. Just means we don't have that last step, right? Because we're adding 0 to all our y values. And so there's only going to be 2 steps in sketching this thing. Okay. So by the same idea, right, we're going to start with t to the power of 3 and then build out from there, right? And so we start with y equals t to the power of 3. And find 3 points to track, to follow around. I'm going to let x be -1, 0, and 1 again, because those are easy to deal with. If x is -1, -1 to the power of 3 is -1. If x is 0, 0 to the power of 3 is 0. If x is 1, 1 to the power of 3 is 1. Okay. So these are the points that I'm going to be following around. So let's see what I can do here. Oh. I'll start at 0, 0, because that's always a nice one. 1, 1. I don't know, let's put it here. And then -1, 1. Or -1, -1, sorry. And then because we know what odd-powered functions look like, right, or odd-power monomials look like, we know that it's going to look something like this sort of S curve. It's not an S, but I don't know why I want to call it an S, but sort of. And so I know that if I connect these, well, it's not very good, but that's all right. Okay. So step 1, we have to add h equals 1/2 to each of the x coordinates. Oh, hello? Okay. So I'll just copy this. Copy. So I can draw on it. Right, if I add 1/2 to -1, so x is -1 here. If I add 1/2, it actually bumps me over this way, right, to the 1/2 mark. If I add 1/2 to 0, right, I'm at 1/2. If I add 1/2 to 1, right, I'm at 1.5, or 3 out of 2. 3 out of 2 ain't bad. So if we're moving over, so we're adding 1/2, we're at -1/2, 0, oh, sorry, -1. Here we're at 1/2, 0, and here we're at 1.5, or 3 over 2. Oh, keep writing 0, but it's 1. So our new graph has points at 1/2, 0, 3 over 2, 1, and -1/2, -1. And again, we just try our best. Okay. Step 2, we have to multiply all our y coordinates by a, right? Our a is 8 over 5. Yuck. So multiply all the y coordinates by a equals 8 over 5. Okay. What's nice here is that all my y's are -1, 0, and 1, right? Those are nice to deal with, right? It could happen that you would have to deal with fractions, right? So you need to be able to multiply fractions, even adding fractions, subtracting, dividing. Oh my goodness. So we'll see where this takes us here. So if we're multiplying the y coordinates, the x coordinates stay the same. And so -1 times 8 over 5 puts us at -8 over 5, which is what? 8 over 5. Who knows? Nice. Better. Or at least for me to deal with. So that puts us at -1.6. Okay, so here it kind of goes and scooches down a little bit, right? So we're at -1/2, and it kind of -1/2, -8 over 5. 1/2, and then 0 times 8 over 5 is still at 1/2, 0, phew. And then same deal here, 3 over 2, and then 1 times 8 over 5 puts us at 8 over 5. 3 over 2, 8 over 5. So we've got this point, 1/2 is 0, 3/2, 8/5, and -1/2, -8/5. Connect these. Whee. No. I will redo that one. I'll blame it on the scale too. No. Just didn't start well. How about if I do this? Start from the other way. It's hard. We can double check with Desmos. Where'd it go? There. Boom, boom, boom. Do you guys remember that song? Boom, 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 boom.
You said not sing out of the word.
Well, so, thank you. So we'll do 2x minus 1 to the power of 3, and it's only because Ash and I were trying it out that I know I need double brackets, right? But also to get that fraction in there, I put double brackets and then 2x minus 1 to the power of 3, and then end those brackets, step down, and then end those brackets, and then divide by 5. We can check. 1/2 0. So far, so good. 0. What about at where were we? -1/2. Oh, there it was. Negative, it's really hard. -1/2, it was -1.6. Do you guys see it? Yeah. Anyways, we can do the same thing here, just to double check, but there she be.
How do we, when we're doing this ourselves, how do we tell how sharp the elbow is supposed to be?
I know, how do you know, right? No, it's just, so for me, as long as you're keeping track of 3 points, right, and showing me how they're moving, right, and kind of, I'll give you a grid, right, so then it'll be easier to do, but, right, that's all I care about. So as you can tell, I wish I could draw like that, but I can't. Yikes. So it's, yeah. But as long as you're keeping track of those points and you're showing me that you know that the general shape should be like this and not some weird, like, kind of choppy line. Well, maybe this isn't the best idea, but, or best graph, but as long as you're showing me that you know the general shape of it, then that's fine.
You barely show every graph.
Yeah. So for this, I'll get you guys to do it on an assignment and maybe on a test. I don't know. But then I'll give you grids for each of them, and you'll have to show me all the steps, right? Because I'm looking at the steps, I'm not actually looking at the graph. We all probably have Desmos installed by now. We can kind of do it pretty quickly, right? We can look at these graphs, but for us, it's kind of the math and the procedure. Yeah. Okay. I think I forgot to do, oh, well, step 3 is nothing, right? Step 3 is add k equals 0 to each of the y coordinates. Done. Yeah, but we're moving 0, so. But yeah, so that's what we would do, right? So now, if we've got the domain, or if we need the domain is going to be negative infinity to positive infinity. And the range is the same, right, for odd powers. Missed some riveting stuff. All right. So let's talk about just straight up polynomials, unless there are questions before we do it. All right. Polynomial functions. I suspect that I forgot to do the domain and range for the last one. I did. I'll squeeze it in. The domain, negative infinity to positive infinity, and the range is what? Up to y equals 3 and everything below it. So from, sorry, start the other way. Negative infinity up to 3 inclusive. Sorry, yeah, you'll have to flip back, but I forgot. Polynomial functions. Woohoo. A polynomial function is a function of the form f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus all the way through to a sub 2 x squared plus a sub 1 x plus a sub 0. All those a's are just denoting the coefficients, right? So they're not really doing anything, and then x is to the power of n, and then decreasing powers from n. Right? So just leaving room for any number of terms, but also any power. Where a sub 0, a sub 1, all the way up to a sub n are real numbers. And n is in the set of natural numbers, which we know now is just 1, 2, 3, 4, blah, 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 blah. The domain of a polynomial function is, again, negative infinity to positive infinity. Oh. Some terminology, pun intended, because they're all terms. Terminology. And it just dawned on me. Terminology. N is called the degree of the polynomial. The degree of the polynomial. A sub n, x to the n, is called the leading term. It's called the leading term. You could probably guess that a sub n is the leading coefficient. And a sub 0 is the constant term. Just some kind of housekeeping. If f of x equals a to the a sub 0, right? So if it's a constant, and as long as a sub 0 is not 0, right? So it's a constant term. We say f has degree 0. Another thing, if f of x equals 0, we say f has no degree. Those are just not important, but good to know, right? And so we'll be talking about the leading term, the leading coefficient, the constant term, all that kind of fun stuff. And so we've already looked at some polynomials, right? We've looked at a constant function, right? So we have already looked at polynomials. Right? A constant function is something like f of x equals a sub 0, right? That's the 0th degree. A linear function looks like f of x equals mx plus b, right? Which we could rewrite as a1x plus a sub 0, right? So this is the first degree polynomial. And we looked at quadratic functions. Which we can write as f of x equals, we've been writing them ax squared plus bx plus c, right? But we can rewrite that as f of x equals a sub 2x squared plus a sub 1x plus a sub 0. Right, so now we're looking at a second degree polynomial. So we've already seen a few. How about we do an example where we're just identifying leading terms and the degree and all that kind of fun stuff. So find the degree, the leading term, the leading coefficient, and constant term for a f of x equals 4x to the 5 minus 3x squared plus 2x minus 5. This one's fair enough, right? The degree is just the highest power of x, so usually we want to make sure that we write polynomials in the order of decreasing powers, right? Because we want to know what that leading term is. And so we'll start with the degree. I'll just do d is 5. The leading term is the whole thing, right? The whole shebang, 4x to the power of 5. The leading coefficient is the coefficient of x to the power of 5, which is 4. And the constant term is negative 5. What about if we do g of t is 12t minus t to the power of 3? You'll want to make sure that you rewrite this so that the powers are decreasing, right, in order to identify the leading term. Right? And so we'll rewrite this as negative t to the power of 3 plus 12t. And now I know I have degree 3, right? That's my highest power. My leading term is negative t to the power of 3. My leading coefficient is negative 1. And my constant is 0, right? Because all of the rest of them have t's in them, so they're not constant. Not too bad. What about if we have something kind of harmless like h of w is 4 minus w over 5? You'll want to rewrite this. And we had to deal with this, I think, maybe with linear equations, right, where we had to kind of rewrite this in the form of y equals mx plus b, right? But when we have, then we can list them in order of decreasing powers of w, and then we can identify the degree, the leading term, the leading coefficient. So as easily as we brought these two fractions together, we can pull them apart. We can say, well, 4 over 5 minus w over 5, right? As long as they both stay over 5, it's safe. And then I want to have my powers of w decreasing, so I'm going to rewrite this as negative w over 5 plus 4 over 5. Here, I can identify that my degree is 1, right? My highest power of w is 1. My leading term is negative w over 5, or negative 1 over 5 times w, right? If you prefer to have the coefficient and then your variable. Makes it easier to figure out what your leading coefficient is. In this case, it's negative 1 over 5. And your constant is the 4 over 5, the one that's not attached to a w. Yeah. How about P of Z is 2z minus 1 to the power of 3 times z minus 2 times 3z plus 2. Yikes. We could make this an exercise in expanding, right? Or we can say, well, I know how expansions work, and what I'm going to have is I'm going to have 2z all to the power of 3, and then I'm going to multiply it, right? So you take the highest power from each of these, right? So your z is always on this side here, so you've got 2z to the power of 3 is later going to multiply by z, and then by 3z. We can cheat and skip expanding this, right? If we recognize that as long as we multiply all the highest power of z from each of these terms, right, we're going to have our leading coefficient or our leading term. So we can cheat and skip expanding this if we recognize that the leading term, because we're not asking about any other terms besides the constant, right? But we can actually do the same thing with the constant. If we recognize that the leading term will be the product of the highest powers of z from each term. I'm calling them terms. I don't like it, but I can't think of the word. Maybe it is term. So for example, 2z to the power of 3 times z times 3z is 2 to the power of 3 times z to the power of 3 times z times 3z. So we get, well, we know 2 to the power of 3 is 8 times 3 is 24. 24, and then z to the power of 3 plus 1 plus 1, we get 24 times z to the power of 5. And just for fun, you could go through and you could expand that whole thing. I don't know about you guys, but I love expanding stuff. I find it very soothing. So something nice and big like this, I don't know, seems fun. But just take your time, write them all out. Anyways, but your leading term is going to be 24z to the power of 5. So from here we can pull our degree, we can pull our our leading term, and we can pull our leading coefficient. So now we know that the degree is 5. Our leading term is 24z to the 5. Oops, should rewrite that. And our leading coefficient is 24. We can apply a similar method to find the constant. Right. Take all the constants from each of these. So we've got negative 1 to the power of 3 times negative 2 times positive 2. Negative 1 to the power of 3 is negative 1 times negative 2 times 2, which is 2 times 2 is 4, is the constant. So C equals 4. Okay. We can do it. I'm supposed to talk about the end behavior, but I think we're okay. I'll just summarize it here. So what happens with polynomials and the graphs of polynomials is that the end behavior, so regardless of, everything in your polynomial, you could have a huge polynomial, but the end behavior of a polynomial is going to match the leading term, right? So you can just look at your highest power, and if you have an even power, then you're going to have this kind of end behavior as long as A is positive. If you've got an odd power, you're going to have this kind of behavior. Well, I mean, it's hard to do. Well, maybe like this. You're going to have like this. I don't know. Hand-eye coordination. Right? So the type of behavior that's going to happen at the ends, right? Things will happen in the middle, right? It won't be that nice, straight, kind of flattened surface anymore. There might be some activity in there, but the end behavior of any polynomial will match the highest or the leading term, right? The highest degree. So since a polynomial is a sum of monomials, the graph will depend on the individual terms but the end behavior will always match the leading term. So if n is even, right, then we might have something that looks like, and we don't know what it looks like in between, right? But it's going to look kind of like this if A is greater than 0, or like this if A is less than 0, right? If we've got a negative A. And if n is odd, we've got kind of this action if A is positive, if A is greater than, oh, changed it, greater than 0, and the opposite, kind of going this way, if A is less than 0. Anything can happen in between, but at least you know how it's going to behave at the end, right? And so for try f of x equals x to the 3 minus 75x plus 25. And y equals x to the 3 in Desmos. So let's give that a go. We've got x to the power of 3 minus 75x. Oh. Start broadcast, I don't know. I don't know why I did that. I overloaded it. It's feeling like you guys maybe. X to the power of 3 minus 75x plus 25. Okay. So we can zoom out and see what it looks like, right? And then on another line, I'm just going to put x to the power of 3. Okay. It doesn't look the same, especially if you're looking here. That doesn't look the same at all. In fact, it's hard to see. I wonder if I can pick a different color. I don't think I can. I've used up all my colors. But at the end of the day, despite that kind of weird activity in the middle, they take off and have the same end behavior. Right? Hard to see, I don't know. Can I go like this? Nah. Anyhoodle. They behave the same. Woohoo! Let's start. No. Do you guys want to do another example? Or do you want to go to hydrology? Those are your options. I know, I'm worried because I won't finish it, and then you'll have a long weekend. And I hope it's really good, and everyone feels better when you come back. Anyways, I'll see you on Tuesday.